All right.
Professor,
Yes.
I just want to ask.
Okay. So the question was about gravity, whether it is related to charges or things like that. Okay. So what we know now from our present day understanding of matter in general, okay, of the atoms as well, okay, is that each elementary particle, okay, for example, an electron is an elementary particle, a photon is an elementary particle. Now, a proton is the sum of elementary particles, okay? But let's say each elementary particle in the known matter that constitute matter, okay, has basic properties. And there are three properties. One is mass, the other one is charge, and the third one is what we call the spin. But let's forget about the spin for a second. So basically what I'm trying to say, each elementary particle has at least two properties, mass and charge, okay? So depending on the mass and the charge, okay, this gives you a certain particle. For example, an electron has a charge negative and a mass m, okay? Now, a positron has, which is the antiparticle of electron, has the same mass but opposite charge. Okay, a photon has zero mass and zero charge. So if you build these, say, what are the different combinations that you can have in terms of mass and charge, then we end up having several particles, okay, which constitute our world, you know, our known universe, okay? So now the way I explain the electric field, okay, and the electric field line as shown here is actually quite similar to the effect of gravity. I would like to just take a few moments here to tell you what's general relativity. I don't know if you guys have seen this general relativity. Well, I think that most of you know that, or were taught that if I take this pen, okay, and I leave it, of course, it will fall. All right. Now, the origin of this, of course, was the apple with Newton, okay, and at least listen carefully, the invention of the force. So what Newton did, he invented the force, okay? He invented this concept of the force, and what we say, okay, you know, what you've been taught, this pen, there is a gravitational force, okay, acting on it. This gravitational force is equal to its mass multiplied by a gravitational field. This gravitational field is caused by the total mass of the Earth, and of course, this is at some radius r from the center of the Earth. Okay, so I think that all of you, and what we use in everyday life, we say, this one has a weight equal to mg, I leave it, then ma equal to mg, and thus it has an acceleration, it falls, it starts from v equal to 0, it will have a v different from 0, consequently there's an acceleration, okay? It falls down, and well, you know, everybody's happy and things were great, and we were able actually to solve 99% of the motion of planets around the star, and the motion on Earth, okay, the acceleration, etc., velocity, positions, etc. This is called kinematics or Newtonian mechanics. Okay, so this is all great until until Einstein came. So Einstein, what he did is that he noticed that experimentally, if you put if you try to apply Newton's laws on the motion of, I think it's Mercury, okay, it doesn't work. It works globally, but there is an error, and this error is systematic. It's not something which is related to the measurement, okay? It's really something which is systematic, and it's a very small error actually, but nevertheless, it exists there. It exists. And so this has brought him to try to understand where this error came from, okay? And as a consequence of this work, he postulated what we call now the generativity concept, or generativity theory, whereas the whole concept of a force no longer exists. So in the generativity, there's no such thing as a force, okay? What there is what is shown here in this graph, if you take a look at it, is a curvature of space-time, okay? So what he says then, consequently, is basically as if you have, if you have your bed, okay, and you have a small ball, okay, and you put this ball on the bed. Of course, it doesn't move, okay, it's still there. But assume that you sit on your bed and you put your ball next to you. What you will see is that this ball will follow the curvature that you made on your bed, okay, and it will go to you. It will move towards you because the curvature is like this, okay? So in this case, what happened? You made the curvature, you curved the space where the ball is sitting, and this curvature, it tells the ball how to move. So for example, it moves towards you. So now there's a different concept between a force, between the two objects. So we have two objects, and then the Earth is attracted to the sun by the gravitational force. It's rotating, so it has centripetal acceleration, and the equilibrium between the two gives you the radius of the Earth, okay? But in reality, this is a simplification, and actually even an oversimplification. But the main reason why we use it all the time, because it really works, okay? For our everyday life, it works, okay? But the generativity tells us there's no such thing as a force attracting to it. There's a curvature, and since the space where the Earth is curved towards the sun, okay, then the Earth will tend to go towards the sun. Since it has a centripetal acceleration, okay, then it will remain on with an equilibrium. It has an equilibrium orbit around the sun. So this is a general relativity. Now, the same thing, okay, can be described using for electrostatic forces and the charge. So if I replace the mass by charge, roughly the same thing, I can describe basically the word in the same thing. But nevertheless, in this lecture, we will still use the Newton's laws and forces and three Newton's laws. But I would like you to understand that it's really, if I would like to explain what is an electric field, okay, I have to bring this concept of space curvature, because it's really like a description of the space curvature, how the space is curved around the charge, okay? And for this reason, I put it. Now, there is an exercise in chapter 1 where you guys are asked to compare the electrostatic forces with respect to gravitational forces. We will come back to this once this is done, once basically Gauss's law done. So basically not this chapter, the chapter after that, then I am, I think that the main part for quiz 1 is done, and then we will do much more exercises. Does this answer your question? Yeah, I think it was a bit long, but I think that it is important that you guys understand these concepts. So the usage of Newton's laws is really much more for its simplicity and its application to our everyday life. We don't need to Every time you want to solve the motion of a particle around another, then you need to take into account and solve the space-time equations. Okay? Okay.
I don't want to get out of.
Excuse me?
I have a lot of. I don't want to get out of topic. I have a lot of questions about this. Can we talk about this after class?
After class? What do you mean after class? Who's talking first?
I mean, I have a lot of questions about these, but I don't want to waste the time of the lecture.
Okay, yeah, let's wait. Don't worry, we will get to it. Okay, I'm not interfering. Don't worry, we'll get to it. Okay. Okay, so electric field lines. Once again, electric field lines, they represent the electric field. They represent the modification, and please, this is very important, the modification of space. Yani, there is nothing, okay, where you have these field lines, okay, this is representation, there's nothing. There's only space. There are no particles, there is no matter, there's nothing, okay? There is only space. So it represents the modification of space by a charge, okay? From a practical point of view, okay, we need to come up with a practical way to draw these field lines. And the practical way, it starts by setting an imaginary test charge, which is negligible positive charge. Okay, so the sign of it is positive, but the amplitude is infinitely small, and it's only in my mind. It doesn't exist really. Okay, but why I would like to do that? Because it will help me draw the electric field lines. Okay, so the electric field lines are drawn by the motion of test charges and not by the motion of real charges. Okay, so this graph here shows the difference between, if you compare B and C, shows the difference between a test charge and a real charge. Okay, so I cannot use basically a real charge to measure the electric field caused by a given by another charge, because this real charge will actually affect the charge distribution on the other charge. Okay, so so basically. This is what we call the electric field lines. Since the charge is positive, so this means that the electric field line will be direction of the electric field line will be away from the positive charge and towards the negative charge. And so this is a schematic. We have seen, I think yesterday, we have seen some of these field lines that we draw here. I don't know if, can you see what can you see, guys? Can you see the PowerPoint presentation or the okay, anyways, I think that I have shown this yesterday. I'm going to move on. Okay, so now the second concept. In this chapter we have three concepts. First concept is the electric field lines. What do they represent? How we draw them? The second concept, and this is extremely important, is electrostatic equilibrium. Okay. It's actually quite simple. When there is no net motion of charges within a conductor, the conductor is said to be in electrostatic equilibrium. Okay. Of course, needless to say that if you charge an insulator, it's immediately in electrostatic equilibrium. You don't need to be, because there are no motion of charges. Okay, so electrostatic equilibrium, no net motion. I will come back to the issue of net. Okay, no net motion means electrostatic equilibrium. If I do not say that charges are in motion in the problem, this means they are assumed to be in electrostatic equilibrium. Now let's focus just a tiny bit about on the word net. Why do we say no net motion instead of saying just simply no motion? Okay. Well, because no net motion, because any object, any electron or any atom in your conductor, okay, is always in motion. Okay, always, and the way what we do to describe this motion is that we use the temperature. Temperature gives you motion. Zero degrees Kelvin temperature, now it means no motion. Okay? If I am a person at 30 degrees, this 30 degrees represent the thermal motion of all the atoms that exist in me. Okay? And actually, that's how you guys can see me. Okay? So, no net motion, this means that I'm not going to take into account the thermal motion of the electrons or the protons. So I'm going to assume that they are still. I'm going to take the average position of these electrons and protons. And on the average, it's still doesn't move. Okay? So this is the concept of electrostatic equilibrium. The more importantly is going to be the consequences for this electrostatic equilibrium. Okay? And here they are summarized. Here I'm going to go over each of them. What do they mean? Okay. So let's take the first one, and that is when I give you a conductor which is in electrostatic equilibrium, or I do not say that the charges are in motion, consequently they are in electrostatic equilibrium de facto. Okay, this immediately means that the electric field inside equal to zero. Okay, let's see how. Let's see why. Well, first we are talking about conductors. Remember, conductors, it means that you have free electrons, right? So each atom, and we determined for copper, okay, each atom of copper has one electron, whether it's on the surface or inside the bond. So everyone, each atom has one free electron. Now, assume that I have a net electric field inside equal to zero, different from zero. If the electric field inside is different from zero, this means each electron is going to have a force exerted on it, which is equal to Q multiplied by E. Okay, because now I have E different from zero. If I have a force equal to Q multiplied by E, this means that these electrons will move opposite to the electric field. All the electrons will move opposite to the electric field. If all the electrons will move opposite the electric field, this is a net motion of the electrons. And since in our definition, we do require there is no net motion, since I'm talking about a conductor, so I have free electrons, the only way that I will not produce motion is to have electric field inside is equal to zero. Okay? So once you are given a conductor in electrostatic equilibrium, immediately you are given, you don't need to demonstrate that, okay? You are given the electric field inside, which is exactly equal to zero. So let's view it in a different way. So before the external electric field is applied, free electrons are distributed throughout. Now, when the electric field is applied, the electrons will move such a way they will cause an exact equal and opposite electric field on the inside. Okay? So what this means that now we will see in a few seconds that the charges will be on the surface and the net electric field inside is exactly equal to zero. Okay? Now the distribution takes about 10 to the minus 15 seconds and can thus be considered as instantaneous. We will not be considering the case where it is not steady state. So we will be only dealing with the steady state situations. I'm going to stop here because I think my time will end on this and we'll be reconvening immediately. Okay?